A governor is the control mechanism that regulates the speed or load of a prime mover, such as an engine or turbine, which is responsible for converting fuel into mechanical or electrical energy. In power systems, governors play a crucial role in maintaining the stability of power output by adjusting fuel or steam input in response to changes in speed or load. This is especially important in power generation where consistent output is necessary to meet demand while avoiding fluctuations that could destabilize the system or damage equipment. The governor uses feedback loops to continuously adjust the input to match the desired speed, compensating for changes in load. Governor components. A modern governor consists of 5 key components. Speed setting determines the desired speed of the engine. In mechanical governors, this is done using a speeder spring, while in electronic governors, it's controlled by voltage or current. Speed sensing. The governor must measure the actual speed of the engine. In mechanical systems, flyweights connected to the engine's rotation sense the speed, whereas in electronic systems, sensors measure the frequency of the generator output. Comparison mechanism. The governor compares the actual speed with the desired speed. If there is a difference, the governor adjusts the fuel input to bring the speed in line with the desired set point. Fuel adjustment. The governor adjusts the fuel input by moving a throttle or valve, thereby increasing or decreasing the power output. Stabilization. The governor must prevent oscillations or hunting in the system by using feedback mechanisms to adjust fuel changes gradually, stabilizing the speed around the set point. Hydromechanical governors. Traditional hydromechanical governors rely on mechanical components like speeder springs, flyweights, and pilot valves to control fuel input based on the speed of the engine. These governors use oil pressure to operate a servo piston, which adjusts the fuel flow to the engine. As engine speed increases, the flyweights move outward due to centrifugal force, lifting the pilot valve and increasing fuel. As speed decreases, the flyweights move inward, reducing fuel flow. Though highly reliable, these systems are slower and less precise compared to modern electronic governors, which can make more rapid and subtle adjustments. Development of modern governors. Over the years, governors have evolved from simple mechanical systems to complex electronic controllers. Early hydromechanical governors were limited by their ability to adjust fuel precisely under varying loads and conditions. As power systems became more complex, particularly in the field of electrical power generation, governors needed to respond faster and with greater accuracy. Since the 1970s, electronic governors have largely replaced mechanical systems, providing improved performance by using sensors and microprocessors to control not only speed and load but also parameters such as exhaust emissions and generator synchronization. These electronic governors are capable of controlling multiple engines, turbines, and generators in parallel, enabling more efficient power management. Droop and load sharing. Droop is a fundamental feature of governors that allows multiple engines or generators to share a load proportionally. In simple terms, droop refers to the reduction in engine speed as the load increases. This intentional reduction helps stabilize power generation in systems where multiple generators are operating in parallel. Without droop, engines would compete for load, causing instability. When a load is applied, the governor reduces speed slightly, which balances the power contribution of each generator. This allows for effective load sharing, as each generator takes a proportional share of the load based on its droop setting. Typically, droop is set between 3% and 5% of the engine's full load speed. Synchronization is the process of matching the frequency, voltage, and phase of a generator with the electrical grid or other generators before connecting them. This is essential to avoid damaging the generator and the grid. A generator must be synchronized before being connected to ensure that its output frequency matches the grid's frequency, and its voltage and phase angle are aligned. If the generator is not synchronized, it could cause large surges in current that could damage equipment or lead to power outages. Modern governors assist in synchronization by adjusting the speed and phase of the generator to match the grid. Once synchronized, the generator can be paralleled with the grid or other generators. Load sensing and sharing. In modern power systems, load sensing is crucial for efficient power management. A load sensor measures the real power in kilowatts being produced by a generator. This is typically achieved using current transformers CTs, which measure the current flowing from the generator to the load, and potential transformers PTs, which measure the voltage. The data from these transformers is used by the governor to calculate the generator's load and adjust the fuel input to maintain the desired output. Load sharing is especially important in systems with multiple generators. Each generator must share the total load proportionally, depending on its capacity and droop setting. If one generator is overloaded or underloaded, the governor adjusts its output to balance the system. Isochronous mode. In isochronous mode, a governor maintains a constant speed regardless of load variations, ensuring that the frequency of the generator's output remains stable. This mode is particularly useful in isolated power systems or when precise frequency control is required. When operating in isochronous mode, the governor makes instantaneous adjustments to fuel input to keep the engine running at a fixed speed, even as the load fluctuates. However, in systems where multiple generators are connected in parallel, isochronous mode can cause instability because one generator might try to carry the entire load. Therefore, isochronous load sharing schemes or droop settings are needed to balance the load across multiple generators. Automatic paralleling systems. Modern power management systems often include automatic paralleling systems, which allow generators to be synchronized and connected to the grid or other generators without manual intervention. These systems use advanced control algorithms to adjust the generator's speed, phase, and voltage before closing the circuit breaker. Automatic paralleling systems improve the reliability of power generation by reducing the risk of human error and ensuring smooth transitions during load changes or generator startups. They also help optimize fuel consumption by allowing generators to share loads efficiently, reducing the overall operational costs of power systems. Governor linkage. The linkage between the governor and the engine's fuel control system plays a critical role in ensuring accurate and reliable governor performance. Poorly designed or maintained linkage can lead to instability, overshooting, or engine damage. For example, if the linkage has too much slack or is binding, the governor may fail to respond correctly to changes in speed or load. Proper linkage design ensures that a small movement of the governor's output shaft results in a proportional change in the fuel input, allowing for smooth and accurate control. Special attention must be paid to the design of the linkage when controlling engines with non-linear fuel systems, such as carbureted engines, where the throttle position does not linearly correspond to fuel flow. In automatic generation control AGC, the modern power governor plays a pivotal role in dynamically regulating the output of generators to maintain grid stability, especially in large interconnected power systems. AGC is responsible for managing the balance between electricity supply and demand in real time by adjusting the generation from multiple power plants to ensure that the system frequency remains within a defined range, typically around 50 Hz or 60 Hz, depending on the region. The modern governor is the interface between the physical generator and the AGC system, translating control signals from AGC into precise adjustments in generator output. When there is a mismatch between generation and load, resulting in frequency deviations, AGC detects these imbalances and sends correction signals to the generators. The modern power governor responds by adjusting the speed of the prime mover turbine or engine that drives the generator. This is achieved by controlling the fuel or steam input based on the magnitude of the frequency deviation or the required correction in power flow. For example, if the system frequency drops due to an increase in load, AGC signals the governor to increase the fuel supply to the generator, boosting its output to meet the higher demand and restore the frequency to its nominal value. Modern power governors, particularly electronic governors, offer high precision and rapid response times, which are crucial for AGC operations. Unlike traditional mechanical governors, electronic governors are capable of receiving and processing AGC signals almost instantaneously. This allows for fine-tuned adjustments in power output, minimizing the risk of overshooting or undershooting the required correction. The governor's ability to make these quick, small corrections is essential for maintaining system frequency and ensuring that power exchanges between interconnected areas remain within contractual limits. Furthermore, modern governors enable participation in frequency regulation and load sharing by responding not only to local speed or frequency measurements but also to AGC setpoints. In a multi-generator setup, where multiple generators are controlled simultaneously under AGC, the governor ensures that each generator contributes proportionally to the total required power adjustment based on its capacity and operational limits. This coordinated control prevents overloading of individual generators and ensures efficient distribution of generation resources. Another critical aspect of the governor's role in AGC is its ability to operate in both droop mode and isochronous mode. In droop mode, which is commonly used for load sharing among parallel generators, the governor allows a proportional reduction in speed as load increases. This feature is essential for multiple generators to share load while operating in parallel without causing system instability. In isochronous mode, the governor maintains a constant speed regardless of load changes, which is necessary in isolated systems or in specific scenarios where precise frequency control is needed. The AGC system can switch between these modes as required by system conditions, further enhancing the flexibility of the power system. Moreover, modern digital governors often incorporate features such as predictive control algorithms, self-tuning capabilities, and remote communication interfaces. These advancements allow them to better integrate with AGC systems, optimizing power plant performance and ensuring real-time communication with control centers. For instance, predictive control helps governors anticipate load changes and respond preemptively, thus improving system stability. The self-tuning capability of modern governors ensures that they can adjust their response characteristics based on operational data, maintaining optimal performance under varying system conditions. The modern power governor is a critical component of AGC, providing the fine control necessary to balance generation and load in real time. Its ability to adjust generator output quickly and accurately in response to AGC signals helps to maintain system frequency, ensure power quality, prevent cascading failures, and enable efficient power sharing across interconnected grids. The integration of advanced control features and communication interfaces further enhances the governor's role in ensuring the reliability and stability of modern power systems.